We're going to start projectile motion. It's a it's a continuation of pretty much everything we've done so far. So this is just a quick little thought thing, and I'll show you a video. But Vet has just spotted an escaped squirrel grasping a tree branch. This is a classic physics problem, except it involves a monkey. I changed it to a squirrel. The vet takes aim with the tranquilizer gun and shoots. The tranquilizer gun makes just enough noise to startle the squirrel, and then the startled squirrel immediately drops down from the tree. They just fall. So the second you shoot the tranquilizer, the squirrel in this case, falls. The scared squirrel, I already said that, but the experienced vet knew to account for the falling squirrel and aimed accordingly before shooting. And then the question is, where should you shoot? Or where should you aim? There's a little simulation of it on my site if you want to go to it and play around with it. I'm going to show you the video. I'm going to try to insert the video, so I'm going to give the answer on the next slide, and then I'll try to either cut that out and put the video. We'll see what happens. So the answer turns out, and then hopefully I can get the video in here, you can see it, is when, let's do it this way. If the squirrel was here, and the tranquilizer was here, and the squirrel let go the second you shot, right? The squirrel would fall, the tranquilizer would fall, and they would, because of gravity that's acting the same on all objects, that's from the free fall, right? It's just going forward is the only difference. So as it falls, they fall together and you hit it. The same thing happens if you're down on the ground. You're gonna shoot at that thing, and as it falls, it's gonna hit the thing.
All right, we got some background music. We're aiming at the squirrel. Now the laser is a little above it, but the laser's above the projectile. So I'm accounting for the projectile being a little lower. But we're aiming right at it. See what happens. Okay. You guys ready?
I found the eagle.
All right, here we go.
I found the pizza.
Yes!
Potato pat. The eagle.
All right, here we go.
And then hopefully I can insert a video there. So projectile motion, like I said, is a combination of free fall, which is and forward motion. So the basketball here is going forward, right? Forward, and up and down all at the same time. And then so vertically there is an acceleration, right? It slows down as it reaches its peak, and then it speeds back up, just like free fall. It's also moving forward, but in the forward direction, it doesn't accelerate. The second it leaves your hand, there is no force acting on that thing. There's no more push. So, and you've never had this happen. You're playing catch or watching somebody throw a ball back and forth. It just doesn't automatically speed up, slow down, speed up, slow down, right? It's nice and steady, back and forth, nice and steady, back and forth. Now it speeds up and slows down, going up and down. So when we're doing these projectile problems, or even the concept questions, vertically is acceleration, horizontally is constant motion. Again, a big gust of wind could come around, and affect the horizontal, but we're looking at a nice, like, calm day, typical day, not a breezy day. Here we go. Combination. So here's the equations. It's the free fall equations again. I know I'm blocking that one. That's just a VY. So free fall equations, and then all we added was the very first equation. So no new equations. It's still the same silly stuff. Now we just need to be more careful, especially when we're doing problems, that we separate the horizontal from the vertical, and I'll show you that when we start doing problems. But anything acting horizontally does not go with the vertical, and anything acting vertically does not go with the horizontal. We'll talk more about that. Jumping and hang time. This is something you can do with your phone. If your phone has you download an accelerometer app, and you can actually, like, put it in your pocket or something. Just make sure it's, like, tight against your body, and then jump up. And then what'll happen is you'll see this big. So this is you just standing there, maybe putting it in your pocket right here, and then all of a sudden you'll see this spike, and then it'll go pretty level, relatively level, and then you'll see another spike. Those two spikes, one was you jumping, and then the other one was you landing. The distance between those spikes is the time you were in the air. And then again, copyright stuff. I can't show you the video, but you could look up some pro athlete videos of hang time and of their hang time of them jumping. It turns out the max hang time for a human is about a second. And again, you can try it out if you want to, but the average person is probably like half a second, just to put that out there. This is just an example question. This isn't human hang time, but how long to the peak if the hang time's 4 seconds? So if an object's in the air for 4 seconds, how long until it gets to the peak is 2 seconds. And we'll talk about symmetry. A lot of physics has symmetry, and then this should make sense to you. The time it takes to get to the peak, right? Gravity slowed you down. Well, what's gravity going to do when you get to the peak? It's going to speed you back up. So the time it took gravity to slow you down is the same amount of time that gravity is going to take to speed you back up. So we can cut these problems in half, solve to the peak, and double some of the stuff to get the answer for the whole trip. Sometimes that just makes things easier. Hopefully that wasn't enough to flag it. I might have to try to cut that out. All right, so the variables real quick. These are, I'm going to have them listed out on the class cake. They're also listed out on the notes for your own. I would have access to them somewhere. Just this chapter, people tend to get bogged down, not with the material, but with there's so many options for variables. Because we're going to have left and right variables, the x variables, horizontal variables, right? Those are all the same. And then we're going to have vertical y variables. So we're going to start out with that, and they add in some stuff like range. Just a word to describe dx, right? Distance in the x direction, or in this case, displacement. These just like free fall, they're going to solve for displacement. I have a bad habit; I'll keep saying distance, but there's no change in direction, so they're going to be the same, but they're not. They're going to give a direction associated with them, which then makes them a displacement. Is how I would put it. So range is distance, but in the x direction, so we subscripted x. Now you could have a dx to the peak, and then that wouldn't be range. That would just be dx. So it would say like, how far to the peak? How far? It might say range. How far horizontally to the peak? It probably could more clearly say, but I guess it could also say the range to the peak. Anyway, height. Same idea. It's a displacement. We want to know how high we are, but it's vertical. So we subscript it with a y. And then again, dy, the height, could be anywhere. We are picking, why I drew the picture this way. There's 3 main areas. There's the initial, there's the peak, and then there's the landing. Those are your 3 big spots. They could ask about the other spots, but those are the big spots. All right, so initial velocity. The variable for initial velocity, it's just vague, right? I don't know if you're shooting it horizontally or vertically because it doesn't say. So we don't have an x or y with it. We just have v with a subscript 0, which is, the naught at time 0. Instead of saying 0, we say naught. But it's v naught. Now, if we want to know how fast we're going initially horizontally, then we subscript it with an x. So then we got vx naught. And then what you can see, or hopefully you can see, is that it's about to make a triangle. Oh boy, here, I'm sorry guys, whatever's going on here. So vertical velocity is v with a y with a 0, right? So vy naught. That one, I like that one. Vy naught. There's vy naught, there's vx naught. Anyway, they make a right triangle. Problem-wise, we're gonna gloss over that. I think it's worth looking. We'll answer questions about angled projectiles, but I think we'll save some time. It would just take a whole nother week, is what I'm telling you. So we're gonna save some time. Maybe not a full week, but more time than I would like to give it. I'll put it that way. And then we'll go on to some other stuff. But so all we're leaving off is that you might have to do some trig stuff, but I don't think that's the end of the world. So what we'll do, and I'll show you when we do the problems, is horizontal projectiles. They're going to start out flat and then fall. Like start flat, fall. And you get the same idea. All right, so that's all the variables at the beginning, the initial velocities there. What happens though is you go up, right? And gravity slows you down to where you hit the peak, and then you drop that zero because we're no longer at the beginning. We're somewhere else. So we're at a final, right? Instead of putting the F, they just drop the zero. But Vy is zero at the peak, right? It's gonna stop at the peak, and then horizontally it's gonna keep going. It never slows down, right? Vx is always going to be equal to Vx naught. So those are interchangeable. Like you can drop Vx and Vx naught are going to be interchangeable. That's at the peak, and then so it keeps coming forward, right? It's going to still maintain that forward trajectory, and then it's about to hit the ground. So what happens is you still got the same Vx. Whatever gravity took away, gravity gave back. As long as it's level, like that line is showing us, then we do get now that technically uh, I didn't have room to squeeze it in there. Those are VFs. This is all VFs, but what I'm telling you is Vx equals Vx naught. So that's because the horizontal velocity never changes. The vertical velocity started out at something. It went up, it slowed to zero, and then gravity gave it back down. So that's why I'm calling it a negative Vy naught. But it is a final. It's the same as the initial, just upside down. Which then makes, if the two sides of the triangle are the same, a squared plus b squared equals c squared, it gives us the same velocity that we launched it at. And this is interesting. And I think most of you, not maybe that you didn't know it out loud, if that makes sense, but you've experienced it where if someone's tossing you a ball and it goes up pretty steep, you know it's going to come down pretty steep. And then that's what's happening there. It's because the velocities are the same. The forward velocity was the same as the initial velocity by the time it gets back to you. And if it's real shallow, you know it's going to come in shallow. I don't think it'll flag me for showing you a website. This is real quick, and it's kind of silly. I'm just going to shoot this thing. We probably use this simulation on some of the problems. There's a couple simulations I use. All right, so we shot that thing, and it makes a nice quadratic, nice parabola. Set initial. All right, so watch. All we're looking at here is it's just a visual. As I go, and I know it's just a simulation, but this is what's happening. The vertical velocity is dropping. See how it's dropping to zero? And then all of a sudden, it just hits zero right at the peak. Now, x is still x. It's still moving forward. If x changes, then it's not going to have that nice curve, which again, really big gust of wind could change everything. But we're talking normal calm day, just throwing a ball back and forth. Like these work. And then so if I keep going, now Vy, right, starts to drop, gravity starts to pull it down. And then there, it's the exact same as it was at the beginning. And then gravity's always down. I know that's from free fall, but all right. Whoop. Amplify. Yeah, so you'll do, I don't know that that's on amplify. I think it's on quiz. It doesn't matter. I think yours is on quizzes. It's just a quick rundown of the variables we just talked about. So you can come back here, you can come to the notes. It's just something we need to practice, and then the problems we'll talk about there. All right, so XY independence. I hinted at this. I said this at the beginning, but I didn't really explain why. It turns out, so horizontal motion is going to be independent of the vertical motion. They are two different things, right? Gravity can't affect the horizontal. So the horizontal motion is not going to be affected by the fall, is what happens. And if you want to try it, drop anything while walking across the room. It lands right at your feet because it maintains the forward velocity. You're driving in your car and you drop something, it just lands at your feet. It doesn't fly to the back of the car just because you're going 60 miles an hour. So there's this video. It's not me, so I can't show it. So it'll flag us. But is jumping. It's a guy. It's a couple people. Anyway, they're jumping on a trampoline while a tractor's pulling them. There's a lot of these out there now. But the question, so would it be safe to jump on a trampoline while it's moving? Well, yeah, because everybody's moving forward at the same horizontal speed. So as long as it's not a gusty, windy day, you're going to keep, even though you jumped up and left the trampoline, you're going to keep moving at that constant speed and land right back on the trampoline. So it's something to look for if you want to. Two marbles. So here's another question. Two marbles will be released at the same time from the same height. One of the marbles will be launched horizontally while the other will just be dropped. So this one's a little tricky to set up. So I don't have it. I don't have it on me. But what you can do, and it doesn't show up. I mean, I could try to record it, but I think it'd be tricky. What you can do is you take like 2 coins and you put them on the edge of the table. So you got 2 coins on the edge of the table, and then just take a ruler and but different positions. So put one coin right near the edge and the other coin a little further back, and then you're gonna give them both a push. You're gonna push them so that they get pushed off the table at different speeds. So it takes a little practice, but if you can get them at different speeds, you're gonna see one of the coins just drop, and the other coin's gonna get a little fat, or maybe not drop, but have a little bit of a push, and the other coin's gonna get a little bigger push. The trick though is to do them at the same time. Uh, and what you'll this verifies XY independence. That forward push has nothing to do with gravity pulling them down. So as long as they start from the same height, they land at the same position. And unfortunately, there's another so would this still work for something faster like a bullet? It does. And Mythbusters, again, this is like a classic physics question. Like you shoot a gun and drop a bullet from the exact same height. Which hits the ground first? Well, physics says it should hit at the same time. Um, I don't know that it was ever actually tested until the Mythbusters did it. So there is a video of the Mythbusters doing it. But if you maybe a bullet myth or something, or what hits first, a drop myth, and then type in Mythbusters. But they set this elaborate thing up where they shoot and it drops the bullet at the exact same time, and we're talking like blink of the eye difference in drop times. But that's just the situation, right? They got wires everywhere. You got to go through air resistance, but it might as well be the same time. Just to put that out there, for as close as we can get it on Earth. There was no atmosphere. They'd land, and there was no delay in the signals between the dropped bullet and the fired bullet. It'd be perfect. But I'm trying to think if there's a Desmos projectile. I don't have a way of showing that one. But I highly recommend taking the 2 coins and to take a ruler and try to push them at different speeds. You'll see them land on the floor at different spots, but they'll hit at the same time every time. It's a cool trick if you want to mess with somebody. All right, Desmo, because they'll think it's the faster or the slower one. I don't know which one I would. I think usually they think it's the dropped one will hit first because it doesn't have to travel as far. But it turns out they travel the same distance because they fall the same distance. All right, Desmo's projectile motion card sort. That one just goes over what we just. It relates forward motion to drop motion, and I'm gonna let you play with that because I don't want to give that away. And it's amplify. I need to fix all these Desmos things. All right, projectile angles. The so conceptually, we will do some with angles because they are interesting. Mathematically, like I said, I want to save a couple days. If you're interested, though, just come Google Meet me and I'll walk you through one real quick. Or my videos are online. Like you can watch me do the angled one. Those aren't locked out from you. You have to go to the YouTube channel, but they're right there. How can a target? So here's the question, and this is I like this for anybody that paintballs. Right? You got people behind a wall and you're just shooting at the wall. You can't get them. So the question, and you estimate that it's like a 30-degree angle to that you're shooting at that wall. Uh, so how can a target be hit that is behind a wall if the projectile launcher can't be moved from its location? So you're pinned down, they're pinned down. You're like, what can I do? Well, instead of 30 degrees, you could shoot that thing at 60 degrees. It's its complementary angle. You got right 30 and 60 add up to 90. And so at 60 degrees, that projectile is going to go steeper, right? It's going to go higher in the air, and then it's going to it potentially could come over the wall. That one I can show you video. That one I made a video of. But here's what happens. How is it that I can shoot something at 30 degrees and 60 degrees or 40 degrees and 50 degrees, any complement, anything that adds up to 90, 20, 70, 10 and 80. Now I'm just showing off. You get the idea. How do they go the same distance? Like that doesn't make sense. So here's my example for you. 12 meters per second at 30 degrees. You're going to do some trig. So sine and cosine stuff. And you get 10.4 and 6. Do the same thing for the 60-degree one, 12 meters per second. But complementary angle is going to give you, it's going to flip them. You're going to go forward 6 and up 10 instead of forward 10 and up 6. So when we do that math, when we do the v equals d over t, we're going to get different times, but we're going to get this. We're going to get different vx's, right? The 31, the lower one is going faster forward than it is up. The higher, steeper one's going slower forward than it is up. So they have different vx's. Time-wise, because the 30-degree one is in the air less, so it's in the air for about 1.22 seconds, you get 13 meters. And we can solve that with free fall, and we'll do that. I know you're excited. So that'll give us time. So that one goes to 13 meters. You can do the same thing with this one, except because you shoot it at 60 degrees, it's going to be in the air for almost 2 seconds, 2.12, but you still get 13. So it's going slower forward, but it's in the air longer, so it still ends up going the same distance. And I'm gonna try to insert that video right after this. That one, you might look up that one too. But if you're ever pinned down, I don't know who goes paintballing anymore. But if they're ever pinned down, like try shooting up and see if you can hit them coming down. Now, if it's a gusty day, I don't know that I'd waste the bullets. But if it's a calm day, you might do it. Complementary angle. So this is just a crazy picture showing what happens. And then we'll answer those 2 questions just as a little practice here. But here's 15 and 75. Sorry, this is a mess. But here's 75. It goes all the way to where 15 lands because they have the same, they're complements. They add up to 90 degrees. Time-wise, though, the short one's in the air, the 15-degree one's in the air for 0.52 seconds, and the 75-degree one's in the air for 1.93 seconds. So even though the 75-degree one's moving forward slower, it has more time to cover that ground. And then, so which angle spends the most time in the air? So you would think it's the one that goes the furthest. But going downrange has nothing to do with time of flight. Time of flight is all gravity. So for gravity, gravity's just a vertical. So all we're looking for is which one is the highest, which is shooting it straight up at 90 degrees. That one gets people. You want it to be one of these 15, 30. It looked like most people guess 45, but it's not how far it goes, it's how high it goes. Some people do guess 75, and that is close. But you can still shoot a projectile straight up. So 90 degrees, we just forget about that. Which angle travels the furthest horizontally? It ends up being 45. On a nice calm day, it's 45. Probably on a breezier, windier day, you probably want to lower that thing so it's not in the air as long, or the air can't affect it as long, and it'll probably be to 45. But under ideal situations, it's 45 degrees. It's a complement of itself. So it has the ideal forward speed and up speed is that 45. All right. Desmos, there is a Wordle review. This is going to be your first Wordle review. You don't have to do, I think it's like seven slides, but it's the same 8 questions asked over and over again. So once you get them right, and there's a check. Each screen has a check. You might get it right the first screen. You might get it right the second screen. Whenever you do eventually get it right, just stop. You don't have to keep answering the same questions over again. The RPG review game, I might post it just so you can play with it. It's just something I do in class. It's the school's guest network. So if you're at home, I believe the Chromebooks are going to block it. If you're at the school and you're on the student network, it should let it go through. I know that sounds weird, but that's just how they set it up. It's an itch.io account, so they had to they let it through, but there's a bunch of restrictions. Desmos projectile motion quiz, and then you won't have to worry about the quiz. All right, I'm gonna try to insert that video, and then we'll do some other stuff. All right, guys.
All right, we got some background music. We're aiming at the squirrel. Now the laser is a little above it, but the laser's above the projectile. So I'm accounting for the projectile being a little lower. But we're aiming right at it. See what happens.
Whoa, that is awesome.
Okay.
That laser.
You guys ready?
I found the eagle.
All right, here we go.
I found the pizza.
Yes!